OH plus NH4 positive, making me NH3 plus H2O, if we can get it to appear. There we go. And that is your final answer right here. Ammonia has a very strong smell. This is one reason why we used aspirators in our first lab when we added ammonia. We added ammonium hydroxide, and it was the ammonia we were smelling, the NH3. Why don't we just leave it out? All right. Now, the cool thing is ammonia, as you bring it into the aspirator, it reabsorbs into the water. And so that limits the smell we had when we had a strong concentration of ammonia. So, next type of reaction. We did synthesis. We did decomp. So next one is single replacement. In a single replacement, we have the element plus an ionic salt in solution. So if you have an element and a salt in solution, that is going to be our single replacement. A lot of times it's a halogen plus an aqueous salt containing another halogen. That's a usual single replacement. Or it could be a metal element plus an aqueous salt. A metal element plus an acid also undergoes single replacement. And the more active element will replace the less active element in the compound. The more active one will replace the less active one in the compound. Yes, sir?
Are you going to go over the answers yes or
Not yet. We will. Yeah, we didn't get through with all of this on Friday, so PS1 and PS2, if you started on them, you're ahead of the game. Yeah. So some of them you probably couldn't do because they were single replacement. Yep. What do we mean by that? So this little sheet of paper gives us some help on that. So we're going to go through the activity in just a moment. Now, metals want to oxidize. So this is what's meant by activity. The first thing is metals want to oxidize. They want to become cations. That means they want to lose electrons. Non-metals want to reduce, become anions. That means they want to gain electrons. So we just have to figure out which one wants to oxidize and which one wants to reduce in a single replacement. Metals and non-metals do not replace each other. So we have no swapping out of a metal and a non-metal. So how do we know which one is more active? This is done by what's called the activity series. The general activity series for metals with lithium on one end and gold on the other. Which one do you think would be more active, lithium or gold? You had to guess. So, gold we know is very valuable. One of the reasons gold is so valuable is because it does not react very much. So, this gold ring, even though it's a white gold, this ring here does not react very much. That's why I have it as a wedding ring. It doesn't react much. It can, but it doesn't react very much. Very little. Yes, sir?
Are you expected to remember the entire activity series, or will you be given it?
The activity series. The only thing you'll be given on the AP test is this piece of paper here. And the periodic table and equation sheet. You will not be given this exact list yet, but I'll show you how to get it. You'll see whether you want to or not. Some people like to memorize it. I personally don't. I don't memorize anything I don't think is important to memorize. If you know this, you don't need that. If you don't know this, that would be helpful. Yes, sir? Hydrogen is in brackets because hydrogen is not a metal. However, it's placed in this part of the series due to its tendency to become a positive one charge. So, it's in brackets because it's not really a metal, but this is where it fits between lead and copper. So, why is this list the way it is? The more active metal wants to become a cation, it wants to oxidize. So, let's look at this list here, right now. Okay? If you look at this list here, you'll see gold is up near the top. AU. was up near the top of the list. If you look at the bottom of the list, what do you see on the bottom of the list? Lithium. Oh, so the list is right here. Yes. It's very convenient. That's why I don't memorize it. But the one thing that isn't on here, let me see if it's on here. I don't think so. Usually it's not. One thing that's not on here is hydrogen. No, well, it's kind of in the middle. There it is. On this one. Lead and copper, yeah. So there's a few things that are not on the list, but the more active ones do oxidize. Now, the general activity series for nonmetals. For nonmetals, the activity decreases as you go from fluorine to iodine. So what I remember is fluorine is the most active of the nonmetals, and then as you go down, decreases activity. And that's a general trend in the halogens. When the alkali metals, the general trend is the most active is here. Okay? The most active here happens to be our lithium. But fluorine is the most active of those nonmetals. So again, this can also be determined in part through this, looking at the F here. Fluorine's position here at the top. And iodine is somewhere in the middle. Yeah. Now, there's a double star here because it's important to know this series. It's also important to be able to deduce it from this table, which you always will have on the AP test, which is nice. So this table here gives us that information, but it gives it in what's called a reduction potential. Okay? So the reduction potentials can give us the information we need. So this reduction potential is measured in volts. It is an electric potential in voltage. V equals volt. It's not affected by the coefficients. So the balanced equation does not change it. However, you reverse the sign when you reverse the half reaction. So these are all called reduction potentials. If you reverse the half reaction, instead of being reduction, it's going to be oxidation. And the charge is going to reverse. If it's positive, it'll go negative. If it's negative, it'll go positive, vice versa. Reverse the sign when you reverse the half reaction. And it's always listed in terms of reduction potential. Now, the half reaction with the most or closest to positive will be dominant half reaction. The one that's closest to the biggest positive will be the dominant one. We call that the winner. Well, you guys all with this? Yes. Okay. All right. So we're now going to look at this sheet here and see if we can look at a pattern on this reduction potential table. So the ability to reduce increases as the voltage becomes more positive. Okay? So the ability to reduce increases as we go up the table here. So you're more than welcome to draw on this one. It's not a reference table, it's just for you to use if it helps you. The nonmetal activity increases as you go up, with fluorine being the most active up here at the top. So if you look at any of these that are nonmetals, least activity, most activity, if they're nonmetals. A lot of these are metals, but that's okay. So for fluorine here, it has the greatest voltage. Its ability to reduce increases because it has the greatest positive voltage. And if you look at the list here, as you're going down the list, that's where the metal activity increases. And Li is the most active metal. That means it has the ability to not be reduced, but be what? Oxidized. So, because the equation here is showing a negative 3.05 voltage to be reduced, it's not going to be reduced. Instead, it's going to be oxidized, which shows a positive 3.05 volts when it is oxidized. So that's why it can oxidize so easily. So here's our general pattern of activity. Our activity series is built into the notes paper that we always have on test, our reduction potentials. So how would we use this in a single replacement? First, we use chlorine gas as bubbled through sodium fluoride solution. So chlorine gas, what's the formula for chlorine gas? Cl2, that's right. It's bubbled through sodium fluoride solution. Sodium fluoride is a ionic solution, so it's always separate, written as its. Now, if we look at our reduction potential table, we see fluorine here is 2.87. Chlorine is 1.36. Okay. So looking at this here, fluorine is more active than chlorine. Okay. Since fluorine is more active than chlorine, fluorine will remain ionized. It will remain reduced. Because it is more active, it's already in its ionic form. It wants to stay in its ionic form. It does not want to become F2. Because it does not want to become F2, no reaction. That will not happen under normal conditions. If we could somehow change the electrical potential, it's possible that could happen, but it would then reverse back to what it was. Technically, for predicting reactions, it's no reaction. Unless you were told a lot more information, which we're not going to get to that part yet. So this has no reaction. Yeah?
So when there's no reaction, do we write this in green again after the yield sign, or do you just write no reaction?
Just write no reaction.
Okay.
That's it. Yep. So on your homework, if it does not react because of the potential table, then you write no reaction. Yeah.
I thought non-metal activity, when you think of it goes down the table, it's getting more negative. Chlorine and fluoride and
The fluoride here, what you're trying to do is get the fluoride to turn into F2. That would be the possible reaction.
yeah.
Okay, but this has a value of 2.87, negative 2.87 to go in reverse. So if you have this, you're trying to get this into that. So that's a negative 2.87 for that to happen. And you're trying to get this into this here. That's a positive 1.36 for that to happen. Because this wants to stay F minus, okay, more than this wants to become Cl minus because of these two number differences. That's why it stays the way it is. It stays as an F minus. If these were flipped, reversed, then you would have a reaction. Look at this. Let's flip it. Let's change it. We have fluorine gas plus NaCl. Okay? So we changed what was the gas and what was the solution. In this case here, F2 to become F minus is a 2.87. Cl minus to become Cl2 is a negative 1.36 when you reverse the equation. F2 is more active than Cl2. So the F2 is more active than the Cl2. Therefore, the F2 reduces and the Cl2 oxidizes, pardon me. So F2 plus 2Cl minus gives 2F minus plus Cl2. The Na is a what? Spectator. Na is a spectator. The Na is a spectator, it's gone, yes. Yeah. Questions? The Na is a spectator here because the Na is not being oxidized or reduced. It's staying as Na plus. So because this is a single replacement oxidation reduction reaction, it's not changing. Yeah.
So the activity is that, or do we say something is more
Cl2 goes to Cl minus.
Not that,
Not that it goes that way.
no, not that F2 goes to F. That's not considered activity.
No, this is the potential, the voltage for this reaction here. For F2 breaking into its ions, the voltage is 2.87. For Cl2 breaking into its ions, it's 1.36. This is more active than this
Wait, but I thought
because it's a higher voltage.
I thought even for non-metals, it's more smaller than
No, the most active non-metal is up at the top. The most active metal is down at the bottom. This is a reduction table. So as you go down, this is the most active metal, lithium, and fluorine is the most active non-metal. Yeah.
How do you know that NA is a spectator?
Na is a spectator because Na's charge does not change in the reaction, and it is aqueous the whole time, so it's not involved in electron transfer or becoming anything different. So it's same formula before and after. Yeah. Because it's aqueous and because its charge does not change. Na plus does not change.
How do you know, like, if you have to compare it to F2 compared to Cl minus?
Uh-huh.
Or compared to F2 and NA?
So how do you know not to compare it to Cl minus? These two are non-metals. This is the only metal. So it has to be the non-metals that are switching positions. If you had two metals and one non-metal, then the non-metal would be the spectator. You compare the two metals. Uh-huh. It has a larger reduction potential. Okay. So that's a larger reduction potential, so that means it wants to go from F2 to F minus. Because you were trying to turn this into this. When you try to turn this into this, these are the two competing ones. 2.87 is bigger than 1.36, so that's why this wins. The F minus does not become F2, so it just stays F minus. That's why the other one had no reaction. It just happens to be on the chart. Yeah. Just happens to be on the chart in between. All right. Let's try this one. Okay, we want to predict if the reaction occurs, and if it does, what the equation is, of course. So, please write down the equation for this possible single replacement reaction. Yeah. Yep. Cl2 is here, so Cl2 to become 2 from Cl minus. If that were to happen, it's 1.36. But the single replacement to predict the results of the list when you balance. When you just have a single replacement, it's much simpler. Yeah. No. It's the opposite when you're dealing with metals. Copper is equal to silver. Because down with metals, more active, less active. The copper is more active, so it'll switch out the silver. Both of these, Cu wants to become Cu plus and this is less so that's why it becomes copper 2 to copper 1. let's look at the reaction. Now with metals, activity increases as you go up the table. Down. So that's the top, least active. That's the bottom, more active. So as you go down here, this is more active. The copper is more active than the silver. So that means the copper will replace the silver in the reaction. Copper will oxidize because copper is more active than silver. So copper will oxidize. It will go from its solid state to its copper plus 2. What will it do? Which one of these? Well, this is lower down, so this is the most likely state for it to become copper 2 plus. Okay? It will become copper 2 plus, not copper 1 plus, because this is more active. Copper 2 plus state is more active than the copper 1 plus state here. Most active, copper will ionize, will oxidize. Which copper ion will it be? It's going to be the one. So when will it be the other one? Let's look and see. To know which copper ion it will be, we have to use our table to determine the reactions. So first thing you do is you locate any half reaction containing the reactants you want. So these are the actual steps for determining how we know it's copper plus 2. We may know it's copper plus 2 because of our fuzzy wuzzy lab, but that doesn't help us, right? Copper plus 2 because of the fuzzy wuzzy lab. But that doesn't help us on any other problems not dealing with copper 2. So the first thing is our half reactions. These are the half reactions that could happen. Silver, copper, or copper 2. Silver plus 1 electron gives us a silver solid, copper solid, or the copper solid here. We see these voltages here. We know that this is probably the most active form of copper, and then this one is the least active because it's, again, top of the table. Nitrate is not in the table, so that means it's a spectator. Another in. Yes?
Copper 2 is always more active than how could you ever have copper 1?
Ah, good question. How could you have copper 1 if it's always more active? Depends on what it is. Depends on what it is reacting with. So in general, you tend to have copper plus 2 more often. But the difference of voltage is not much. So if you have, again, difference of voltage that accounts for that, you get copper 1. So let's see how we would know which one it would be for sure. You want to reverse any half reaction, so your reactant is the reactant of the half reaction. So which one would we have to reverse? The copper or the silver? The copper. You want the copper to be plain, so it could be either one of those. We can reverse those. So there's our silver, there's our copper, there's our copper. Okay. All right? Now, what do we do next is the next question. The half reaction with the most positive voltage is the dominant half reaction. Most positive voltage. So we just looked at these three here. So out of these two, which one is the most positive voltage out of these? Alright? Most positive. So let's look at this. The most positive one, of course, is our silver, which we didn't forget about. Okay? And the silver here, is it oxidation or reduction, this dominant reaction? That's reduction. So it's reducing to its elemental state. Now to determine which one is being oxidized, see if we can go, there we go. Determine amongst the remaining reactants, find the most likely complementary half reaction. Complementary half reaction is with most positive electron voltage is the next dominant half reaction. Next dominant. So we know that's reduction. So now we need the complementary oxidation half reaction. The one closest to positive voltage. So that is our second one. And there is our oxidation half reaction. Copper going to copper 2 plus its 2 electrons. Now you need to add the half reactions together and balance them. So this is where we adding half reactions together. We follow the rules that we know for half reactions. So right now we've got all elements other than hydrogen and oxygen balanced. We don't even have hydrogen and oxygen, which makes it nice. So all we've got to do is make sure that the number of electrons on each side is the same. So 2 silver, 2 silver. That changes the 1 electron to 2, and that is your final answer here. So that's how you use the chemical information and the reduction potential table to determine the reaction. God bless you. Yeah. How come you don't write the electrons? Because when you put a 2 here, a 2 here, and a 2 here, the 2 electrons cancel. Make sense? Yep. So, at this time, let's write down our 5 steps here. So, half reaction containing your reactants. First thing is to identify the half reactions. So, there's only 5 steps. So, once you identify the reactions, most of this is identifying what's going on, identifying what is not in the table. So, 1 is finding the half reactions. Identify them. 2 is to reverse. Okay. Any half reaction so that it matches your reactants. So reverse the sign for each one as needed. Then the half reaction with the most positive. Okay? So find the first dominant. Identify whether the dominant half reaction is oxidation or reduction. Once you identify that it is reduction in this case, for example, you now have the first reaction here. Then you want to find the most likely complementary. And you do that the same way you found the dominant one, the one closest to, most closest to positive electron voltage. And that is how you find the final one. And step 5, of course, is to add the half reactions together and balance them, of course. Which takes us over here, but fortunately we don't need most of this, just the electrons. Although you can imagine they could put this together if they really wanted to. Kind of mean right now, but yeah.
So if there were oxygen or hydrogen in that equation, would you have to do the adding water?
If you were at that point, you would, yeah. But that would be it. That's the next step forward. What do we do when we get, that's, well, they classify that as redox. This is technically redox, which is a lot of yeah, okay. Yeah, you have to reverse it first before you bring it out. Match it up with the equation. I think I made mistakes in the equation. You have to match it up with the equation. You want to reverse the one you Thank you. All right. The next type of replacement is a specific example. This here is called hydrogen replacement. Okay, for hydrogen replacement, all of these below lead, everything below hydrogen, they oxidize in acid to produce hydrogen gas. So if you have an acid and you're adding one of these things, they will produce hydrogen gas. They will oxidize. So if you toss lead in an acid, boom, hydrogen gas. Nickel, hydrogen gas. Sodium, hydrogen gas. All the way down. Iron, hydrogen gas. Now, the ones below chromium, ones below iron, these oxidize in steam to produce metallic hydroxide and hydrogen gas. So you might want to just highlight these or note these on your on your reduction potential table. Iron.
From where down?
Iron 2. All the way down. Okay. And the third group below sodium. These are pretty cool because they oxidize in cold water to produce soluble metal hydroxides and hydrogen gas. All of these here, sodium and below. Yes, sir? How cold is cold? Room temperature is cold. Yeah, if you take sodium and put it into room temperature water, when we look at the activity series of metals in more detail, it produces an explosive mixture. Yeah, I thought the same thing. Cold water. How cold it's done. But not at 100 degrees Celsius for students. There is a range, though, for sure. You always have things that are in between. The reason these words are important here is because guess what they use on the AP test? Acid, steam, cold water. Doesn't tell you what temperature, just says cold water.
So
Yes?
except the acid passes all the way down to
Yeah,
water area.
exactly. So you can have these here that oxidize in acid, and all of these could, potentially.
So what about this stuff in like the middle or at the bottom?
If you had steam, they could oxidize. If you had acid, they could oxidize. If you had cold water, they could oxidize. So, again, there's a range. All of these would oxidize. Lithium, you got to put it in acid, boom, it's going to oxidize. You put it in cold water, it's going to oxidize. You put it in steam, it's going to oxidize. You put it in almost anything, you got a little trouble. It's a very, very, very active metal. Yeah?
So cold water has ice below boiling point?
Usually it's just called cold water when you're doing a reaction prediction.
You're not gonna like.
No, you're not going to be specific. Yeah, they won't tell you. I mean, they might, I guess, if they really wanted to, but I don't think they do in AP testing. All right. So here are some examples of hydrogen replacement. How would it be written? What would it look like? So here's copper metal placed in 8 molar hydrobromic acid. So what's the key word in this? Acid and copper. So acid and copper. You look back, oh my goodness, I can't remember what I wrote down. Where's copper? It's above it. Uh-oh. So copper is above that point. Less active than hydrogen. Hydrogen will remain ionized. No reaction. Boom. There you go. You knew that was coming, didn't you? No. Not on there? No reaction. All right, let's try zinc metal.
And also oxidize lithium. Oh yeah. Nobody.
All right, first of all, will it react, yes or no? Yes, it will react. So, we've got hydrogen gas produced. Hydrogen gas is produced. We've got the Zn left over and the Br left over. Br does not change, so Br is the what? Spectator. So let's eliminate our spectators and balance the net ionic equation. Yes?
I don't understand why hydrogen remains ionized.
It remains, why it's in here.
Oh no.
Up here it remains ionized because copper is less active than hydrogen, H2, on the list. So, based on the position on the reduction table, the hydrogen here, copper is above the hydrogen. Because of that, the hydrogen is more active as a metal when it's acting as a metal, because copper and hydrogen. Because you go down, boom, it doesn't happen because your hydrogen is below the copper position. So when that happens, it remains as a I minus. So if copper was more active, copper metal would want to become ionized. But the hydrogen is more active. It wants to remain. It wants to become ionized. It wants to lose an electron. Since it wants to lose an electron, it wants to become oxidized. It already is oxidized. So boom, it wins. It doesn't want it. It's not going to change back into H2 because it doesn't want to go backwards. It already is at the state it wants to be at, so to speak. Does that make sense? Okay. All right. Let's try nickel metal. Please write your equation for nickel metal placed in water. All right. How many say react? No reaction. Survey says Ni is less active than H and H2O. No reaction. No reaction. What about Cu in water? No reaction. Very good. You stick copper in there, you stick nickel in there, don't matter. No reaction. Right, Jamie? Yeah, Rahul. All right. Don't rub it in. All right, next one.
I don't understand.
Nickel, less active than hydrogen. So, if you look at this, it's down near the bottom here. Your nickel. Your hydrogen is here. Your nickel is under it. But it only oxidizes in acid hydrogen. In order for it to oxidize in cold water, it has to be down here. So technically, it's not this we're looking at, it's the H2O, which is the normal. There's the H2O. There's the H2O down there, nickel is here. And the H2 really is over here. That's where it is. Not the H up there, although the H2O. All right, lithium metal placed in cold water. React or not react? Of course it reacts because it's lithium. It forms lithium hydroxide plus H2. Right? How do you know it's lithium hydroxide? It has to produce H2. So you take what's left over. It could be LiO or LiOH. When it is placed in cold water, it produces a hydroxide. Now, is this right or wrong? Got to balance it. What else do you have to do? Get rid of spectators, balance it out. Is lithium hydroxide supposed to be written together?
No, lithium is
Good separate? Got to separate it out because it is a soluble salt. Write its ions and balance it out. Yes, sir?
How do you know that all the water isn't consumed? But it could be and then it would be solid.
How do you know that all of the water isn't consumed? Probably because it's in cold water. It could absorb the energy produced by the reaction and would not evaporate completely. And the amount of water you would need would be a very small amount. So I can see where you're coming from. We have to assume that cold water is enough water that it's not going to be completely vaporized. So that's a good question. All right, now we know single replacement, double replacement, single replacement, decomp, and synthesis. Now let's combine some together. Reactions can occur in sequence. So in sequence, you have more than one reaction occurring in sequence. You need to watch out for water as a potential reactant. So if we had something like lithium metal is placed in a solution of magnesium chloride. Lithium metal is placed in a solution. The solution has to have what in it? Water. So you've got Li plus Mg plus Cl and water. Not listed as it's placed in water, but it's placed in a solution, so water is present there. Because of that, we get hydrogen gas produced and lithium and hydroxide ions in solution. You also still have magnesium and chloride ions that are still in solution. So the water reacts with the lithium, and now you have lithium ions and hydroxide ions. The hydrogen gas is a gas, it will leave this solution, but the magnesium and chloride could react with the lithium and hydroxide. The Mg and the OH come together to form magnesium hydroxide. The Cl cancels because it's the same on both sides. And the lithium does not cancel because it's lithium metal here and lithium ions here. So the chloride was our spectator. Then our magnesium and our hydroxide can come together to form a solid. Yes?
Isn't the magnesium technically the same on both sides? How come that doesn't cancel here?
It doesn't cancel here because these two come together to form a solid. Magnesium hydroxide is a solid, insoluble. Solubility rules. That's the only way. Yeah. Lithium versus what? Lithium's at the bottom. Which one are we comparing? Magnesium? Yes, I believe. Well, the magnesium isn't a metal here, it's an ion. They're trying to predict whether these two would. The lithium reacts with the water, first of all. before it reacts with the magnesium. Before it switches places with not always, but in lithium's case, yeah. But you could have a case. Well, they're either going to react with water or they're not. They won't do a replacement reaction and then react with water. Yeah. Because here you need MgOH2 for this to be a neutral solid formula. So that's what makes you go backwards to balance it out. And you also have 2H2 here. So both of those, 2H2 and 2OH, means you have to have 2 waters. If you have to have 2 waters, you have to have 2 lithiums. So it's the 2's in here and here that cause you have to balance it out. Oftentimes when you get H2 as a product, you're going to have to use some coefficients anyways. So that's just a heads up, because usually your H2 is not found. H2O is HOH, 1H and 1OH. So if you write H2O as HOH, you can see that balancing part a little easier. Now, how do we get good at these reactions? Okay, practice. Lots of practice. Now, it's just not just practice today, tomorrow, and a little more practice on the weekend. Lots of practice throughout the whole year. So, we are going to practice these. Remember to write net ionic equations, canceling the spectator ions. So you always want to write your net ionic equations and cancel out those spectators. Balance charges. Charge on the left has to equal the charge on the right, otherwise it's not going to work. Always make sure it's balanced. Especially when you have oxidation and reduction happening or single replacement happening. At first, this is very important, at first, not only try to predict, but also write the type of reaction. Identify, is it single replacement, is it synthesis, is it decomposition? If it's more than one, obviously you're going to be noting each one. This will help you in realizing what product to form. If it's synthesis, you're going to have one product. Decomposition, you're going to have multiple elemental products or compound products that are neutral. If it's a single replacement, you're going to have one that's an ion and one that's not if it actually reacts. So every reaction, all right, so at this time, we've got a few minutes. I know some of you are having challenges with how to approach your lab. Your lab is really good for practicing balancing redox reactions. Okay? In the lab, we saw the purple solution turn clear. The purple solution was our MnO4 minus ion. It was purple. When it became Mn plus 2, it became clear. Okay, that was it being reduced. So you want to pay attention to the electrons, especially. Electrons, we know, have to be equal in a redox reaction. So these steps work pretty good. I will give you a hint. If these steps aren't working for you, start with the electrons and then work your way backwards. So next few minutes, you can work on those things. Practice PS1 and PS2. Lab 4. It's what it says online. I don't think it's due Friday, but let me check. Next week, yeah.